On April 20th, 2004, at around 3:30 p.m., a temporary retaining wall collapsed during excavation for the new Nicoll Highway MRT station. Within seconds, the ground gave way, swallowing a section of the highway. 4 workers lost their lives, and the highway remained closed for 7 months. It was one of Singapore's worst construction disasters. But what led to such a catastrophic failure? The construction of Nicoll Highway station wasn't unusual. It used the same cut-and-cover method as stations like Clarke Quay, Bugis, and Lavender, and the main contractor had years of experience in deep excavations. On paper, nothing seemed out of the ordinary. Initially, construction proceeded smoothly. Workers installed diaphragm walls, drove king posts, constructed jet grout piles and board piles, then added struts to brace the excavation as they dug deeper. But before long, the first warning sign appeared. On 7th August 2003, at Launch Shaft 2, the retaining walls deflected more than twice the predicted amount. Excavation stopped immediately, and emergency measures were quickly implemented to stabilize it. The incident triggered a thorough design review. The authorities' advisory panel warned that Method A, the chosen design method, had overestimated the strength of the marine clay and, as a result, underestimated the wall movement. They strongly urged switching to Method B, a more conservative approach, and reassessing other parts of the project. But the contractor pushed back. They argued that the authorities had no right to dictate how the work should be done. After all, they had been awarded the contract, and their methods seemed to be working well in other parts of the site. After weeks of back and forth, a compromise was reached. Method B would be used, but only for a limited reanalysis, and only for the deeper sections, known as Types K and E1. By October, the reanalysis was complete. According to the findings, it seemed to vindicate Method A. In fact, Method A appeared to match site observations even better than Method B. So, Method A remained in use, and excavation continued under close monitoring. By January 2004, similar issues appeared in Types K and M2. Wall deflections once more surpassed the design limits. This happened only 3 months after the reanalysis of Type K, casting serious doubt on the earlier reassurances. Unlike the previous incident at Launch Shaft 2, safety procedures were not followed. Even after deflections exceeded trigger limits, no effective safety measures were in place. And when the design levels were breached, no comprehensive review was done. Instead, the back analysis for Type K simply reused the original wall section and soil profile. The input parameters were then adjusted through trial and error until the calculated deflection profile matched the inclinometer readings. The results created a false sense of accuracy that did not match the actual soil conditions at Type K. This was not an isolated case. It was later revealed that the back analysis for Launch Shaft 2 and for the sections that followed had been manipulated in the same way. Rather than addressing the root cause, the back analyses focused on proving that the existing design method did not need to change. As the Committee of Inquiry put it, the contractor was performing a mathematical curve-fitting exercise without any engineering basis. It was a complete departure from the true purpose of a back analysis, which is to ensure safety. Soon after, in February 2004, the same issues struck again, this time at Type M3, the very location where the collapse would begin. As the 6th level struts were being installed, excessive deflections were observed. Several stiffener plates had buckled, and one of the whalers had even failed. The contractor responded by replacing the double plate stiffeners with C-channel stiffeners from the 7th excavation level onwards, hoping to strengthen the connection. No one on the contractor's construction or design team had ever used C-channel stiffeners before. The design calculation itself was flawed, and because it was never properly checked or verified, the change was still approved and implemented. While the modification did slightly increase load capacity, it came at a bigger cost: reduced ductility, making the structure more prone to brittle sway failure. In early March, the back analysis for Type M3 was completed. Based on its findings, the main contractor proposed raising the allowable wall deflection limits and relying on close monitoring. The authorities agreed, and excavation pushed forward. But at the same time, complaints from neighboring property owners surged. The authorities and contractor shifted focus to handling those complaints and carrying out urgent repairs. As a result, less attention was given to monitoring and site conditions at the excavation itself, and it showed in the data. By the end of March, the revised design value had already been exceeded when excavation reached the 9th level. Yet, on 5th April, the authorities still gave an approval in principle to proceed to the 10th level, even though the second back analysis had yet to be submitted. 10 days later, on 13th April, an urgent meeting was called. The authorities had brought in an external expert to review the design after mounting concerns from earlier incidents at Launch Shaft 2 and Type K. What he revealed was shocking. The expert found serious flaws in the design method itself. If excavation went beyond 25 meters, he warned, failure was a real possibility. His message was clear: stop using the current approach immediately and reevaluate the entire design. The contractor agreed to look into it. Yet, on 19th of April, just one day before the collapse, the contractor submitted another back analysis for Type M3 and Type K using the same design. They proposed raising the wall deflection limits further. This drew heavy criticism from the authorities. On that same day, another issue surfaced. A massive 8-bay section of excavation at Type M3 had been left unstrutted, putting additional stress on the already fragile retaining system. It was an oversight that would have consequences within hours. By the next morning, 20th April, the first sign of troubles appeared. From as early as 8:45 a.m., workers in Type M3 heard loud metallic thung sounds as whalers at level 9 began to buckle. An urgent site inspection was carried out, and excavation was temporarily halted. During the checks, they discovered something alarming. No inclinometer readings had been recorded for the past 2 days. Even so, the situation was deemed to be serious, but not urgent enough to stop work and evacuate. Just weeks earlier, similar buckling incidents at other areas had stabilized after remedial work, so they assumed this case was no different and decided to try the same fix again. They stopped for lunch at around noon. By 1 p.m., the long-awaited inclinometer readings finally came in. The results were far worse than expected. The wall deflections had exceeded the revised design limits by more than 22%. Remedial work began immediately, but within half an hour it was clear it wasn't working. The whalers were already too distorted for the cement to settle properly, and some were so tilted that it simply flowed out. Then another red flag appeared. The strain gauge readings showed a reversal of how the system should behave. The load on the level 9 struts was decreasing, while the load on the level 8 struts was increasing. It puzzled both the authorities and the contractors on site and hinted at something going very wrong deep within the retaining system. Meanwhile, conditions on site kept getting worse. More whalers at level 9 buckled, and by 3:15 p.m., even the whalers at level 8 were beginning to give way. Still, work continued. Some workers, fearing it was unsafe, refused to carry on and left the site, but no order to evacuate was given. Then, at about 3:30 p.m., it happened. The connection at one of the level 9 struts failed, and one by one the others followed, triggering a chain reaction that tore through the temporary retaining wall and brought it crashing down. Workers scrambled to escape as the ground gave way beneath them. But getting out wasn't easy. Although safety briefings had been given, evacuation drills were rare and poorly remembered. One worker said it took him 10 minutes to get out, climbing between C-channels and support beams because there was no continuous walkway or direct way to run. To make matters worse, hoardings erected to divert grout-blocked access to the emergency siren. This left them no way to sound the alarm. As the ground gave way, a 30-meter deep ravine ripped open, swallowing 2 container site offices, heavy machinery, and a section of Nicoll Highway. Gas lines ruptured, sparking leaks and fires on site, while nearby buildings were plunged into darkness. Storm drains and water pipes burst, sending torrents of water rushing into the excavation. By 4:30 p.m., 4 workers were confirmed missing: a site supervisor, a foreman, a crane operator, and a construction worker. It was later found that the foreman, also known as Hero Heng, stayed behind when the temporary walls at his work site were toppling, just so that he could make sure that his 8 co-workers managed to escape. Rescue teams battled unstable ground and rising water as more than 160 SCDF personnel worked around the clock for 4 days. But heavy rain on the 4th day caused water levels to surge and the soil to loosen, leaving structures too unstable to continue. The operation was called off. Hero Heng's body was never recovered. The highway stayed closed for 7 months, disrupting thousands of daily commutes and forcing major road and public transport diversions. The Nicoll Highway station itself had to be relocated, and it took another 6 years for the station to be open to the public. This collapse tells us a bigger story. It is undeniable that mistakes were made, but they were shaped by the system itself. One way of unpacking this is through an event causation technique, ECT diagram. It starts with a chain of events, traces back to the direct causes, control failures, and uncovers the underlying factors of the disaster, management failures, and the absence of strong safety leadership and culture. One clear example of these management failures was the issue of dual appointments. For this project, the same person served as both the qualified person, QP, and the authority's project director. It was an inherent conflict of interest. This conflict showed up in his actions. After the Launch Shaft 2 incident, he assured the authorities that there was no problem with the temporary works, even though he knew there were design concerns. He admitted he feared that raising them might stop work. He also asked the project team to review excavation procedures so the works could be expedited. In the end, progress took priority over safety. Another clear failure lay in the selection and monitoring of subcontractors. The instrumentation supervisor and technician were appointed without any verification of their qualifications or relevant experience. Their expertise was assumed based on irrelevant credentials and only superficial on-the-job exposure to instruments. Supervision of their work was just as weak. For 3 days before the collapse, no readings were taken at Type M3 because the inclinometer was covered in too much soil. Nobody cleared it. The instrumentation supervisor merely relayed the problem, and the instrumentation engineer did nothing. Yet, on the day of the collapse, when readings were urgently needed, the soil was cleared in minutes and the data retrieved. This shows easily the problem could have been solved days earlier. A third failure was the lack of safety and technical expertise. The very software used to design and analyze the earth-retaining structure was not fully understood by those relying on it. Neither the contractor nor the authorities had the depth of experience needed to interpret its results with confidence. It also didn't help that the main contractor appointed a civil engineer with limited structural design experience as the temporary works professional engineer. Instead of providing independent oversight, he relied entirely on the contractor's design team. He admitted that he did not see it as his responsibility to personally check the designs. A fourth failure was ineffective communication. On the morning of the collapse, the Strut subcontractor's site engineer and foreman raised safety concerns and objected to continuing work at the base of the excavation. Their warnings were ignored, and remedial works went ahead without the subcontractor's project director even knowing. Within the authority, the design team technically had the power to issue a stop work order, but they were unaware of this responsibility. They assumed the contractor would act when design limits were breached, and no procedure existed to check whether work had actually stopped. Within the main contractor, the construction team failed to pass on clear warning signs such as the buckling of whalers to their own design team. Escalating risks were never reported to senior management. But behind every management lapse was a void where a strong safety culture and leadership should have been. There was a lack of an informed culture with the entire project. An informed culture is one in which those who manage and operate the system have current knowledge about the human, technical, organizational, and environmental factors that determine the safety of the system as a whole. One of the key features of an informed culture is that senior managers proactively seek out safety-related information and monitor key indicators of major hazards. C824 had a definite lack of informed culture because site problems were not reported to senior managers. The authority's project director was unaware of repeated deflection breaches, missing inclinometer readings, buckled whalers, and even the meeting on 13th April that had already deemed Method A unsafe. The contractor's project director also missed warning signs, despite receiving daily deflection reports that clearly showed excessive movement. Even the safety department, whose job was to oversee emergency readiness, admitted they felt no anxiety on the day of the collapse, a stark sign of how disconnected the safety chain had become. That breakdown in oversight opened the door to a far more troubling trend. A culture of violation took hold. Procedures meant to protect workers became optional, trigger breaches were ignored, and back analyses were manipulated. Relentless production pressure fueled that blatant disregard for safety. By April 2004, the contractor faced $25 million in liquidated damages. They had won the job with a $275.7 million bid, $67.7 million lower than the next closest offer, leaving their profit margins razor-thin. Under intense schedule pressure, high-risk shortcuts became routine. Corners were cut in back analyses, construction was rushed, and quick-fix remedies piled up. Even the authorities felt the pressure. The project director himself had suggested reducing the number of excavation blocks, despite being aware that block excavation was a safety measure against over-excavation just to expedite the excavation work.
The late Professor Trevor Clance warned that accidents recur because organizations have no memory. When lessons fade, tragedies return. Investigation alone is not learning. Learning means remembering and changing what we do. The Nicoll Highway collapse was one of Singapore's most serious construction failures. It revealed weak safety leadership, inadequate controls, and a complacent safety culture. Since then, Singapore has made major improvements, tighter oversight, and a stronger commitment to safety. But organizational memory fades. People move on, priorities shift. That is why we retell these stories, not to assign blame, but to prevent the next tragedy. Workers build the homes we live in, the transport systems we rely on, and the places we gather. Their lives depend on whether we remember or forget. Safety isn't built on regulations or paperwork. Safety is built on memory and the will to act.